very nice experience. So I don't know if there is the laser pointer. Actually, I don't have the pointer.
This one?
Yeah, and we need to start the presentation, I guess. Excellent. Actually, yeah, here we go. So, of course, the title of my presentation is Quantum Computers Can Be Built, and I'm not viewing myself as a quantum optimist. I'm actually think I'm a quantum realist. I first want to pay tribute to the research environment in which I'm at home, and that is the Center for Mathematics of Quantum Theory and the Quantum for Life Center. And then actually one of my colleagues, Bergfinn Odurhus, who may actually be in the audience listening, is the person that connected Martin and me for this. So thanks a lot, and we're eight professors, assistant professors, and about 40 postdocs and PhD students working on trying to understand the theory of quantum computing, including quantum algorithms, quantum fault tolerance, what will be topic of the day, and also applications of quantum computing to the life sciences, but also other applications of quantum technologies in communication, etc. But let me dive right into the talk. I want to actually give you first a background of what is quantum computing, to somehow put a footing under this debate. After that, I want to tell you how I believe, or how the community believes, we are building a quantum, or we can build a quantum computer. And then I have maybe a few points about the debate, and then I'll pass over to Gil. And I understand afterwards we battle in some way, some civilized way. I hope we try to be extremely civilized and you know, put a tie on even today. So what is quantum computing? Well, I mean, before we talk about quantum computing, I can move this virtual laser pointer. We have to understand what is computing and what is information even. And so the unit of information that we're all familiar with, I guess, is the bit. It's a 0 or 1, and the bit is the abstraction. It's an abstract concept. It's really independent of implementation. And so a bit can represent the light switch that's on and off, or a smiley that's smiling or sad, or it can also, the information in our computers, of course, is coded in bits and held in bits. Now, Shannon and Turing in around the 1940s, they said that all physical information can be represented by bits. So in some sense, this is the opposite direction of abstraction. So you say like, okay, whatever I see, whatever, I can always encode it in terms of bits. And this really is the basis for the digital revolution that we see since then. In computers and communication, but you might even go further and say like the information in our brain or even in the universe. And here I draw you a little abstraction of the internet. Now, what is computation? To kind of become more specific of information, in computation you usually start with a problem, a computational problem. Then you're going to buy some hardware, maybe that's your laptop. Then you're going to buy some software or program it yourself. That's over here. And then you hopefully get the solution to your problem. And what's really important here is that hardware and software, they sort of like go together. And you know, we all know the names of a few big hardware companies, and the same is true for software companies, and I think you can sort of like imagine what it is. There's something important about computation is that some problems, they're easy, and some problems they're difficult. And that's of course true if you think about it like naively, oh, that was an easy problem, that was a difficult problem, but there's a formalization of this concept of easy and difficult in theoretical computer science. So here's an example. Multiplication, for instance, is easy. So 5 times 3, that's 15. I think we all learned it. I wrote it like the computation you do in your head. Now 71 times 11, maybe you can also do it in your head. Can anyone shout out the number to get you awake? Just louder. Okay, 781. Very good. What about this? All right. So you need pen and paper to do it, but I think even though I gave you these numbers and they're fairly long, it's hard to do it in your head, but actually it's quite easy to do on a piece of paper, if you remember your kind of primary school algorithm. And the runtime of this algorithm is the number of digits squared. Okay, if you can also ignore the square here, but it's roughly proportional to the number of digits. Okay, so it's pretty fast. So I give you a number, like that basically, it's this lower number is yeah, it's still quite easy to do. So, all right, it takes you a little longer, but within an hour at least, I'm sure you have done it. Now, let's look at the opposite problem of factorization. So I give you 15, and I say, like, give me the factorization into its factors, and you will of course say, oh, it's 5 times 3, right? Now I'm going to do it with the others, but so let me blind this out so I can use the same numbers. What about 781? You still remember it, no? Yeah, it's 71 times 11, but I'm sure you won't remember this one unless someone has a photographic memory. And because actually, if you were to try, so what is the algorithm to solve it? The algorithm to solve it, essentially, is to guess, I really have a hard time dealing with this laser pointer, is to guess the solution, right? And then to verify back with your multiplication algorithm, right? That's the way, but there's exponentially many numbers. So even if you only need 1 second if you can do one entire multiplication up there per second, then it would still take you 60 years to figure out that these were the factors, right? So, so that's really a difficult problem, and the algorithm that we have that I just explained has a runtime that's exponential in the number of digits, and since Corona, I think everyone knows what an exponential is. All right, so. So that's basically the difference between an easy problem that goes polynomial or just like proportional to the number of digits and a hard problem that goes exponential in the number of digits. So what is, so that was sort of my computer science introduction. What is quantum information? Well, so we said before, let's remind ourselves, well, in information we have Shannon-Turing, all physical information can be represented by bits, right? So we had this, and we can also, like if we have the position of a particle that's either to the left or to the right, we can also represent it, right, by a bit, like the position, and maybe it's left or right, that's 0, 1, etc. And also if we have an atom, and I'm coming from Copenhagen, so there was Niels Bohr, and Niels Bohr's model of the atom, you see here that you have an atom and then you have the electron can go, or this is in the hydrogen atom, it can go around either in orbit number 0 or in orbit number 1, right? So also this I can represent with 0, 1, but then we know, and actually already longer than Turing and Shannon, that this is not the whole story, because in quantum mechanics, which describes the atom precisely, you can actually have a superposition, so it can be 0 and 1 at the same time. So it's not 0 or 1, but also sometimes 0 and 1. And that actually means that Shannon and Turing's idea goes out the window and has to be replaced by Deutsch and Feynman's idea that all physical information can be represented by quantum bits. Okay. So, and basically that means things that can be 0 and 1 and 0 and 1 at the same time. And that is what is now known as the second quantum revolution and leads to quantum computers and quantum communication. And you can say everything is quantum information in that sense. And we can have a debate about that. And here is our quantum internet of the future. All right. So we had Margrethe Vestager visiting, and she was, at the time, she was vice president of the European Commission, the Danish commissioner. She's actually the one responsible for dishing out these huge fines to Google and all of the other big IT companies, if you've heard about it. And she visited us for actually 2 hours, and afterwards we made a little quiz. So we tried to see if she knew what a bit was.
Okay, yeah, we'll take it from there.
Let's try it.
Now I have to look at the AV personnel there. I don't know how to activate it.
So what we should do?
Yeah, she will speak to us, hopefully. But,
No, the normal bit. If
Sorry?
So it's either 0 or it's 1?
No, she's Margrethe Vestager. She's the was the former vice president of the
Well, the fascinating
European Commission.
thing about a qubit
And
is that it can be both.
now we don't hear this.
It doesn't have to make a decision to be either or.
Sorry.
It can be both. I think a lot of humans would be very envious that you don't have to choose. You can be both at the same time.
Yeah, so you see there's still some classical computing problems to solve. We can make endless jokes about this. I cannot do a headstand. I would have done it otherwise. It was kind of nice. I can do it later. But will we fix it? No pressure. But we can start the debate. Gil, if you have any things that like you disagree, you could already voice them now. So far, so good. Okay, okay. But we can also kind of continue if you want.
One may give it a try.
We'll give it a try.
So in fact, the idea came to me about this debate in several occasions.
Maybe you should use the microphone.
Oh yeah, maybe. Let's say it's maybe an opportunity to say how it all began. There were several sources. One of them is wife of my dear friend Ron Aharoni from Technion in Haifa, Israel, but also it's Merav Aharoni, but also once in the Land Society we visited a huge computer center, and there they somehow boosted how great computers they have, and they also mentioned that they have quantum computers. And then I said that quantum computers don't exist. And they somehow the director of the center, I was exaggerating, of course, but only slightly, and the director of the center waited 10 seconds, and then he replied, quantum computers do exist. And that's basically the question of this debate. Let's settle it out. Let me ask how does it look like? Does it look with quantum computers and non-quantum computers? We are not sure. But how about the presentation? No presentation, right? So let's skip. I suggest then to skip the presentation and go on with the rest of your talk.
Let's just continue, yeah. Okay, but you can watch the video on my website. All right, here we go. Right, what is quantum computation? Well, I mean, really the same story, right? Instead of classical hardware that you have to buy, now we call hardware classical hardware, right? I mean, your laptop and I don't know what. We call it quantum hardware, so now we need quantum hardware and we need quantum software. It means quantum algorithms. And then hopefully we get a solution, and actually more so than in the quantum hardware part, in the classical part, we need actually a good collaboration between people developing the software and people developing the hardware. We can also talk about more about that later. So let me give you this slide about easy versus difficult that we just had before, right? Reminding you that multiplication was really an easy problem. Every one of us can do it. Supercomputers do it. But factorization is difficult. It's so difficult that it's not only hard for you to do, it's not only hard for your pen and paper, it's hard for your laptop, it's hard for a supercomputer, okay? So this notion of like runtime here is sort of like robust. It's robust to the notion of to the computing device. Okay, so it just means how it scales if I give you more compute power. Right? This is why it's very nice, a very nice kind of way of quantifying it. Now the quantum computers this was the story for the normal computers. By the quantum computer now, actually, this factorization is just as easy as multiplying. And that is an algorithm that Peter Shor from MIT developed in 1997, Shor's famous factoring algorithm. And the runtime, it got easy. And the runtime it takes is the number of digits cubed. Okay? And this is really remarkable. So what we want to do is, of course, build this machine now, right? And we want to run Shor's algorithm. And, you know, we can talk about applications, but it's not the topic, so I'm going to kind of like go on. So which problems are easy more generally? Is everything easier now, right? Can I take any problem and like invert it and it becomes easy? Well, let's look. So we know that factoring is easy. That was Peter Shor. We have also we also know that the problem of searching something, for instance, in the internet or in the telephone book, can also be sped up, not quite exponentially as the other one, but somewhat. And then there is one application that quantum computers are good at. Well, they're good at simulating quantum systems. Okay, and a molecule targeting to a protein that is actually a quantum mechanical process. So maybe they're good at this, and there is good quantum algorithms for simulating molecules. And what is the idea behind all of these algorithms? Well, the idea is really that normally when you have a normal computer, you ask it a question. For instance, you give it the numbers and you give it in terms of like some binary string here of zeros and ones, and then you get an answer. And you know, that's your normal computer. That's how it works. And a quantum computer, you can actually do the thing that you can ask it all the questions at the same time. Sounds marvelous, right? And you get all the answers at the same time. The problem really is kind of that this intuition, you know, this means like, oh, it's fantastic speed up for everything, right? But the problem is you get all the answers at the same time. Well, it's hard sort of like to figure out which answer fits to which question, right? So you're in some sense, this idea or intuition that now 0 and 1 can be at the same time means I can ask all the questions at the same time. It's a nice intuition, but it's not quite correct because we don't think everything gets faster through a quantum computer. So what actually has to be done is you have to have some really clever quantum algorithms designer that comes up with a really carefully crafted quantum question, and that will look a little bit like doing something in superposition, and then you'll run this quantum algorithm and then you'll get this correct answer faster, but not for all problems, but only for some of the problems. So there is some software, quantum software ingenuity that has to come in addition to building the quantum hardware. And if we now go into this quantum machine room a little bit more, then really you have this algorithm from Peter Shor, and for instance, and it will be presented to you as a so-called circuit. So as something that is made up of smaller units, and those smaller units we call gates. These are like small operations, like switching a light switch and maybe like 2 light switches in independence. So, and in a quantum way, okay? So, yeah, it's really difficult, this laser pointer. Yeah, and so any circuit that is presented to you can be represented in these 1 and 2 qubit gates. And so here's the example of Shor. So Shor's algorithm uses a bunch of subroutines here as well that you can see there. Maybe, you know, it's like it touches you know, some of these wires, and then it does some other routine that in itself is called the quantum Fourier transform that can be represented again in smaller ones, and it does some exponentiation down there. Can also be represented in smaller ways. Yeah, it's sort of like how it works. So the question really for the debate is, now that we're all fired up and want to factor numbers, is like, how do we build this quantum computer? And so what we have to do is kind of now the opposite again, right? We have to kind of like take these abstract quantum bits and represent it by physical quantum bits. So really this way, from the 0 and 1, we have to build these things. Well, atoms were actually good at this, right? So we could take atoms directly, like these neutral atom based, and these are actually one contender for building quantum bits. We can also do ions, so that's just like atoms where you took an electron away. And we can trap those, and there's a picture of one of these ions here. Or you can build like artificial atoms by basically taking like an electrical circuit and cooling it down very far down to very close to 0. And now you need to, now this is 1, right? 1 bit, but you need many bits. So many quantum bits. So you you build many of them, right? And then you need to operate on them. So you need to enact these gates, right? And these gates are kind of, you could, for instance, shine with the laser on 2 of the atoms, 2 neighboring atoms, and then they execute some gate. And this is sort of the way, or here in the superconducting one, it would be microwave pulses that you send down some wire, and then you let them interact in some way. Okay, maybe here in the ions, they maybe can move collectively in order to enact some gate. Right? So there's different ways of like how doing these gates, and this way, what is important is to understand that whenever you do this, and this is why this is a difficult undertaking, you need high precision control of single quantum systems, right? Whether atoms, ions, like single quantum systems, and this is not easy to do. But I believe possible. Here's an example from Copenhagen. You can, in the group of Eugene Polsik and Jean-Baptiste Beguin, they are building a machine like this, and they have some atoms here on the top, I think rubidium, and then they let them drop them down, and then they catch them down here, and it looks like this. It's amazing. It's an amazing experiment, and you have this cloud of atoms, and you can capture them in like torches, small lasers. Actually, if this was a real laser, you could capture the atom with this small torches, and then you can move them around, and you can do this computation. And actually, in the fall, and we're not going to repeat this here now, I was invited to a EU Health Summit, and we actually did this live. Okay, so I was like live. This is just a shot from this. I was live controlling the experiment in the lab. And it was a lot of fun. It was very demanding on the AV guys, I can tell you. And I was writing in the array of atoms the pattern of the EU, like EU. Okay, live for the audience there, and with Jakob here in the basement of the Niels Bohr Institute, which is the physics department of our university. And that was a lot of fun. So we do have this high precision control. Maybe we don't have enough yet, or maybe we want to do it better. But there is a path to that. But there is a challenge, and the challenge is the noise. And because entirely noiseless operations and gates are unrealistic in the near future. Maybe they're always unrealistic, but the question is how good can you get them? So let me see what happens if you have a computer where the individual gates are noisy, right? So, it's made up of gates, and then, there may be noise striking in between. And then, of course, well, maybe you're unsure about the solution, right? Now you can't trust this thing anymore. You don't know where the noise happened, and so on. And you're not sure about the solution. Maybe you can still verify them in this case of factoring, but it's not. You don't want to verify the solution. You want to get the right solution, right? And so it doesn't really compute the right solution anymore for you if there is noise happening in the circuit, and the circuit is it's somewhat advanced, has a number of gates. And so. The qubits and the gates, they have been steadily improving over the years. And the noise is well understood and modeled. And actually you can here's an example for these three for these 3 platforms. There are more platforms, but I just took those 3 here as an example, and also the manufacturers, I took them as an example. So you have these superconducting platforms. For instance, IBM here is a big player in the game. They have one machine called the Heron, a 156-qubit machine. The gate error is 0.3%. That means when you basically switch a light switch, right? If you think of a quantum version of a light switch, then with 0.3 probability, then it will make a mistake, right? So if you now imagine you take this 1 bit and you flip it 300 times, right? Then you're certain to have an error. Okay? So even though you know it's pretty good, okay, 0.3%. I once actually had an office where my light switch was not very reliable. It was very annoying, and so it's also annoying here. And it's better in the ions. There are few of them, but the error rate is better. And then the contender really that was overtaking on the right at the moment is the neutral atoms on a very, very promising path. And that is also the one where I showed you the experiment. So, sorry? Yeah, so I don't have a gate. They don't have a machine where you now have a gate error. You can operate the machine in a bit of a different way, but I couldn't find now good numbers for this to put there. But they also have a gate-based machine. And, yeah. So how can we combat the noise, right? So I tell you, it's not going to go away. It's going to go smaller and smaller, and it's on a very good path. It's not going to go completely away. So we have to do something. And the way, what to do is to basically take a bunch of these noisy ones and then simulate a single qubit which has less noise. Okay? This is amazing if this works, right? So you take many of the noisy ones and you can kind of like bunch them together, and some more you get fewer but better ones, and those we call logical qubits. But I would like to say there's a qubits that are not with zero noise but with less noise, so it's always kind of like a trade-off there, but you have to spend some of these physical ones but not very many to get these better logical ones. So here's kind of how you think about it. So you have the logical ones are blue now and the physical ones are red. So for instance, this here is now 7. You can use the minimum number. You can use 7 as the so-called Steen code. Use 7 to go for one logical one. And then the error rate will go down, actually, like quadratic. So you do this, and then, of course, but the number of qubits somehow blows up, but only modestly. So it's all okay. That's sort of like the idea behind this. And there is a threshold theorem. I'm not going to give you too many details. If you want, I can say. So if the noise, and the theorem says, it's a mathematical theorem, it says if the noise is low enough, it's below a threshold, it's a fixed number, it depends on your architecture and on the type of noise, etc. But you know, think of it as being a % or something like that. If you're below that, then actually this simulation works. Okay? Then on this noisy machine, you can simulate these noiseless or qubits qubits with less noise, and then you can run your Shor's algorithm there. Okay? So if the noise per gate is below a threshold, then a noiseless quantum computation can be efficiently simulated on a noisy machine. And this is theorem.
The ones you wrote there, are they below the threshold?
Yeah, it's now a difficult question, because it depends on you need to implement a number of steps, and so you also need to implement, for instance, feedback on them. And there is a number of these steps that we don't have that yet, right? So, but from nominal numbers, some of these numbers, depending on architecture, are lower than the threshold. Yes, but you need to execute certain steps in order to do it. Yeah, so I think I'm supposed to wrap up, right? Yeah, but I have this nice picture. I think this is what you should remember. So I give you this these noisy qubits, these red ones, okay? I give you many of them, then I can kind of like encode my input and the output such that if the errors happen on this real machine, it simulates the noiseless quantum computation on the right. I think it's a very nice picture. All right, the debates.
You can continue. Actually, Gil just donated you some minutes.
Some minutes. Ah, but no. What happened? No, don't switch my presentation off. I still have a few slides for the debate. Huh. What happened there? Ah, yeah. So I think the first thing, it's maybe also still like trying to build a common ground for the debate, is this question of when is a quantum device, okay, a quantum computer, right? Before we debate whether we can have quantum computers, what is it? When is that? So quantum devices, you know, these are some qubits that have been built, and the number is increasing, and there is something called the universal gate set, namely these interactions, that you can do all of these interactions. This has been demonstrated, and the quality of these gates is steadily increasing. And this, I think, is called the De Vincenzo criteria in some sense, and I believe they've been satisfied. Now, when can we call a quantum device a quantum computer? Well, we could do this now. I think actually it's a valid point. We could just say we have quantum computers, because you can actually go online, you can try them out, etc., etc. Well, why not? Because these De Vincenzo criteria are satisfied. I think it's a valid standpoint to take, but I think it's not the standpoint we will be taking for the debate. I think for the debate we probably want to take the standpoint, when are the building blocks for fault-tolerant quantum computing? When have they been demonstrated? Okay, so I think the research community is waiting for that moment. Okay, when we would say, hey, the building blocks for fault-tolerant quantum computing have all been demonstrated in one platform, not one criterion in one and the other one in another one. And so we're waiting for that moment, because then, in principle, we should be able to scale up. Okay? And we should be able to talk about a quantum computer. And actually, maybe I should have started with that. If you think about it just for your normal computer, when would you call a computer, right? It's like when it has 1 bit, when it has 2 bits, or when it has like a C64. Was that a computer already, or is it first your laptop now? Is it first a supercomputer, or when was it a computer? You know, I think it's still like an interesting question. In any case, so the logical, I think we're sort of like at the cusp of this, that the logical qubits are better than the physical qubits. And there are many indications, there are many sort of like different steps and the different platforms that have to be done. And really, I think we're sort of like at the threshold of doing that. And and then there is, of course, the scaling of the number of logical qubits. And I think arguably we don't have that yet. There is a second, last point to this. When is a quantum device a quantum computer? You can take an even more extreme stand. You can say like, okay, fine, it's a bit academic when the research community is waiting for this fault tolerance has been demonstrated. Now, you could also say, hey, when I have a quantum computation, I cannot simulate on my classical computer. Well, then I have built it. And there is claims out there, and I think also maybe we not talk about them so much, about that. Some people call it quantum advantage or quantum supremacy. There's the one that I like best. It's like, give me this, you know, like implement sure, okay? It's like, if someone factors numbers, you know, that's my personal favorite. Then another one would be like solving chemistry of material science problem. Wow, we would all go, wow. Well, cool, right? Now we have payoff, you know, now we can, you know, like industry is rocking. And then there is a real computer science one, which would be implementing a BQP hard problem. That's sort of like the hardest problem in the class, you know, that a quantum computer can do. You know, then you really demonstrated it. And I think this is very nice. And my standpoint to close this is quantum mechanics is a precise microscopic theory that has been tested in many experiments. Quantum mechanics describes very well the devices I've shown to you and the devices that have been built, including their noise. Quantum mechanics predicts no roadblock to building more and better qubits. And once we have sufficiently many qubits and good enough gates, we can efficiently simulate fewer but better ones, so the threshold theorem. And the upshot, I think we're well on track to building a fault-tolerant quantum computer. It's a difficult endeavor, but I don't think we have indications that it cannot be done. It'll require money, time, and patience, and some high-quality research and engineering. But I think that's what we should do. Thank you very much.
Thank you. Thank you, Matthias, for the realistic view, and let's continue with Gil Kalai.
Okay. I need
Okay, so this was a very nice introduction to the area and to the pessimistic, to the optimistic point of view, realistic point of view. I should say that I will present a different theory. I also share the benchmark to show algorithms. As far as I know, quantum computers, quantum devices can factor maybe 15 to 3 times 5 or something like that, but I don't think they can do better. And also, as far as claims, I must admit that I think my point of view, my argument gives some obstacle for achievements in this direction, but I cannot give obstacle for what people are claiming, because sometimes people are claiming fantastic achievements that on scrutiny are baseless. So let me, okay, so here is our initial stance at the debate, and Matthias gave a brilliant video presenting his point of view that you can find on the site of this debate, and I gave my own video, and I think this discussion could be a nice introduction to our videos. So Matthias, as we heard, he...
Sorry, it seems that this is the right point.
Oh, this is the right point, okay. Matthias thinks that we are well on track, and that for building full-scale quantum computers, we need more and better qubits, and we will look at this stance in a minute. And I think that building scalable quantum computers and even achieving early significant milestone in quantum computation is fundamentally impossible. So I'm not talking about the fact that the hopes for implementing Shor algorithms for 200-digit numbers are going to fail, but some very early milestones that people are trying to achieve in the near future, in the years to come, even them are already fundamentally impossible. Not this one.
It's moving.
It works. Okay. So are quantum computers possible? So quantum computers are fascinating, hypothetical, powerful computers, and the debate regarding their possibility represents one of the most important scientific problems of our time. And my theory asserts that building scalable quantum computers and even reaching significant milestones toward them are fundamentally impossible. So here is a very brief overview of the argument against quantum computers. And this argument is based on analyzing the power of what's called noisy intermediate scale quantum system, or abbreviated NISQ systems. So noisy intermediate scale quantum system represent a low-level computational ability that will not enable quantum error correcting codes that are needed for quantum computation. So here we take a two-scale approach for studying the very same noise models that Matthias talked about, and we analyze the models in the intermediate range. And for them, we find out that we can identify the computational complexity class that represent their computational power. And this is a very low level. And when I say very low level, I mean not only that it's a classical computation, but it's a very primitive classical computation. So quantum computers that people are building these days for tens or even for hundreds qubits before they can, any fault tolerance can apply, they represent classic computation. From the computational complexity point of view, they represent classical computation and even low-level classical computation. This implies that they will not be able to achieve the task that Matthias talked about. They will not be able to achieve quantum supremacy, and they will not be able to achieve something which apparently is even harder than quantum supremacy, which is building good quality quantum error correcting codes. So this is a computational complexity obstacle for achieving this early milestone in quantum computing. There is some novelty here that we use computational complexity reasoning to deduce limits for engineering efforts. And I think Matthias and I think most of the community think that increasing the quality of qubits and gates is just an engineering effort. If the engineers will try hard enough, they can reduce it even to zero. I think Matthias said that maybe we shouldn't expect zero noise in the near future, but people expect that we can reduce the amount of noise or the rate of errors as much as we can. And my argument says this is not the case. There is an obstacle, and this obstacle is based on computational complexity argument. And indeed, this is a new sort of a twist in the usual way that computational complexity argument is used. But this will be tested in the next few, or in the years. So let me make 4 predictions about quantum computers, and I'll try to, I think the important thing is that the content of the prediction will be clear, and I'll say a little bit about the logical relation between them. The first prediction is that there is inherent noise for qubits and gates. And this applies both to physical qubits and to logical qubits. Qubits and gates will inherently be noisy. Engineering efforts to reduce the noise will encounter a barrier that prevents achieving the quality required for quantum fault tolerance. And I think 2-qubit gates are, and this is a point of agreement, I suppose, are especially important. They are important because they seem to be the most difficult, and also they are really needed for universal computation. But in any case, all these qubits and gates are noisy, and there is a barrier for how good we can make them. So this means that the quantum fault-tolerant threshold cannot be reached. Okay, let me make a few other predictions. The second prediction deals with correlated errors in cat state. So one important ingredient in quantum computation is the ability to achieve what is called entanglement. This is quantum correlation between 2 qubits. And my prediction is that when you have cat states, then the errors, then there will be error which will be correlated between them. And let me not get to the mathematical formulation, but again, when we are talking about entanglement which is achieved by gates, I think this is a point of agreement between the two of us, the theoretician and the experimentalist. But what I claim is that this will be inherited for any pairs of qubits for which you implement entanglement. And this is a consequence if quantum fault tolerance cannot be achieved. Now, this prediction is the core of my argument. It says that samples generated from boson sampling, which is a special type of quantum computers, and quantum computers in general in the intermediate scale, correspond to a primitive computational complexity class called LDP. So LDP stands for low-degree polynomial. This is a computational class for probability distributions, and as a result, they are incapable of demonstrating quantum supremacy or achieving high-quality quantum error correction. So this is the crux of the argument. And this argument imposes computational complexity-based limit on the engineering effort to reduce errors. in noisy intermediate scale devices. And this assertion, if you accept it, this is what logically implies the first assertion and indirectly the second assertion. So this is the crux of the matter. And for those of you who are familiar with computational complexity, this class LDP is even much more restricted than what's called bounded depth classical computation, which is by itself a very restricted computational class. And the fourth prediction is that small quantum circuits will demonstrate noise sensitivity. So the empirical distribution of samples obtained from 12-qubit random circuits inherently contains a significant noise-sensitive component. This means that the empirical distributions are necessarily non-stationary, changing over time, and are inherently unpredictable. You can call it chaotic if you want, but technically using the term chaotic makes complicated, make confusing, but they are noise sensitive. And okay, and I should say that there is a theory of noise sensitivity and noise stability which was developed by several groups, but also by myself with Oded Shram and Itai Binyamini in the late 90s, which is relevant to this discussion. And the implication trying to implement it for distributions coming from quantum computers was in a paper with Guy Kindler in 2014. Okay, so let me now mention an important point of this agreement. Number one, well, it's partial disagreement. As you will see, Matthias says that for a full-scale quantum computer, we need more and better qubits. I think the important thing is better qubits. More is less important. And my view is that I agree that we need better qubits and gates, but I argue that it's inherently impossible to build qubits and gates of the required quality. Let me move to a second point of disagreement. Matthias says that I will argue that there are no theoretical obstacles that we know of for achieving full-scale quantum computers. And my view is that I agree that there are no definite theoretical obstacles. However, there are serious theoretical concerns that need to be noted, and these theoretical concerns were raised by others, not only by me. And my theory gives a plausible theoretical framework for the impossibility of quantum computers. The debate will largely be decided experimentally. So some people from my department asked me if there will be a vote at the end of the debate. And I said, yes, I think it's good to have a vote, but let's postpone it to 2040. So stay here and... So let me say a little bit about other skeptical claims. Here you can see in the picture, you can see Michel Diakonov, who is a physicist and very skeptical to quantum computers, and with me. And here I'm with Robert Aliski, who is also has a very skeptical argument from the physical standpoint to quantum computers. Here we are, me and Robert Aliski, in 2005 with Michael Ben-Or and Dorita Aronov, the founders of the threshold theorem that Matthias mentioned. They are good friends and colleagues of mine. And on the two left side, there is Oded Goldreich, who's a computer scientist, and Leonid Levin, who is a computer scientist, and who also strongly believes that quantum computers cannot be achieved. So let me just mention earlier skeptical claims and responses. So for example, the basic claim is that quantum computing violates the extending Turing shared thesis. This is something that Matthias described in a different name. In any case, the Turing point of view for information. This is a reason to believe that they are nonsense. So this is what, for example, Goldreich and Levin says. And the response is, from quantum computers optimist or realist, is yes, indeed, this is a feature, not a bug. We will go beyond the Church-Turing thesis. Another argument, which is interesting one, is that quantum computers is in tension with the time energy uncertainty principle. So this is a certain principle in physics that I don't want to describe. This is a very interesting argument by Alinsky from 2000. And the point of view, or at least of modern quantum computing theorists, is that time energy uncertainty principle is a misconception. Shor algorithm clearly shows that it's false. Another claim by Alinsky is that quantum computing is in tension with thermodynamical principles. And again, the response is, wonderful. We'll be able to use quantum computers to create remarkable novel thermodynamical behavior. So you see that there are physical principles that are in tension with quantum computation, but and I think they are not definite. They don't give definite reason to say that this will not work, but they cannot be ignored either. And as Matthias mentioned, perhaps the most important difficulty is that errors will cause quantum computer to fail. The response is that quantum error correction, quantum fault tolerance will solve the problem. A response to the response is that fault tolerance is based on unphysical assumptions, and this is part of the more technical debate. And again, some skeptics say implementing quantum fault tolerance is ridiculously hard, and the response is no, it's only very, very hard. So this is this summary. So let me, in order to give, let me give a brief assessment of the progress in the last decade. And here I connect to what Matthias described. This is a point of view of quantum computers in the famous David De Vincenzo 7-step road map to quantum computers. And there are several steps. And the steps that is now needed to be achieved is logical memory with longer lifetime than with substantially longer lifetime than the physical qubit. So you need to build quantum error correcting code which are much better. And this task, people, he made this diagram, not this picture, but this 7-step in 2000. And I think until 2010, people really thought that this is coming soon, that they will be able to soon build quantum error correcting codes. Like in Copenhagen, we founded in the Hebrew University quantum computing centers, and I remember a lecture in the first conference, 2013, by John Martinez, who promised to have much better logical qubits in few years. And the fourth step was not achieved yet. And as I said, I think it will not be possible to achieve logical qubits with much better quality than the physical qubit. Around 2010, people had another idea. They said, let's push in between step 4 and step 3, let's push another step, which is let's try to achieve what's called quantum supremacy, or to demonstrate some computational task that classical computers cannot do. And as far as I can see, fantastic quantum supremacy claims are unconvincing. I'll mention one in a minute. And there is a good theoretical, so this was very useful for our research because there is a good theoretical argument by Guy Kindler and myself that quantum supremacy requires quantum fault tolerance. So if you have quantum fault tolerance, we both agree that you can make Shor algorithm and you can achieve things that classical computer cannot do. But our paper argues that without quantum fault tolerance, you cannot achieve quantum supremacy. And this was challenged, this is challenged by several claims. And I think people try to show quantum supremacy or quantum advantage as some intermediate step, which there's nothing wrong with intermediate step, except all the attempts, in my opinion, and we will come back to it in a minute, are not convincing. And then there is another another approach, which is topological quantum computer. And this approach is to shortcut the need for quantum error correction by building for topological memory with much longer lifetime than physical qubits. And this is based on gadgets which are called Majorana zero modes. And so far as I can tell, the claims of Majorana zero modes, there were claims from groups in Delft, in Holland, and in Copenhagen, and in Microsoft. But so far, these claims are not convincing. And therefore, we didn't get, although, well, I'll come to in a minute. So here is the third important point of disagreement. Matthias says that the research is well on track. And here, I don't want to be too negative. So my view is that I agree that a lot of brilliant people are involved in this endeavor, and there are good ideas and innovations. There are, however, also concerns about correctness, transparency, and scientific conduct of some major experimental claims. In general, published experimental claims are often not properly scrutinized. So as somebody wants to study this matter, I advise, look, take your favorite experimental claim and try to scrutinize it. I think Mark Mezard mentioned yesterday that he scrutinized the statistics of some outrageous claim regarding the corona epidemic. But in general, it's important to scrutinize the quality of scientific papers and of experimental claims. So far, my theory is consistent with the outcomes of credible experimental progress. So I would say that the research is well on track, but we don't know where the track is leading. And in some sense, I'm pleased that there is the fact that people invest billions, perhaps even tens of billions of dollars to study this matter, and in my opinion, to verify my theory, is because they don't believe in it they don't take it too seriously. Let me say one word. So there was one paper, and then some by a group from Google that claimed quantum supremacy. And if this was correct, then this would be direct contradiction to what I told you. And this was studied by several groups. So other people, Google claimed that in 5 minutes they make some to a place and he was very hungry, and they didn't, who came to a place and he was very hungry and they didn't want to give him food. And then he said that he will prepare a soup from stone. And there he's a soup from stone. And his hosts were very pleased. Matthias talked about the rate of errors. So far, in the 5 years that passed since the experiment, we cannot get from the Google team, although we were in fairly good relation and we corresponded with them, we cannot get from them the rates of errors for their 2 gates in the experiment, which is, from some reason that I will not explain, is quite important. So recently there were even more fantastic claims. So Google claimed that quantum computers achieved in a few minutes a computation would require 10 septillion years for a classical computer. So septillion is 10 to the 25. So it's even more than 10,000. But you see, there is no prize for making claims. I didn't know what septillion is, but then I learned. It looks, I don't know what Matthias thinks about this claim, but maybe he will tell us. But it doesn't look so promising. And Microsoft, 2 months ago, claimed to create the first topological qubit using Majorana zero modes. And again, it's questionable not only if they created a qubit, but even if they created Majorana zero modes. And these fantastic claims by Google and Microsoft are probably incorrect. So my conclusion is that there are compelling, though not yet definitive, arguments for the failure of quantum computers, as well as for inherent obstacle to near-term goals. And exploring this avenue presents intriguing scientific challenges and could have significant implication for various areas of quantum physics. To say everything I said is in the framework of not only in the framework of quantum mechanics, but in the framework of the standard models for errors that were used in the threshold theorem. So, thank you very much.
Thank you very much, both of you. Very nice. So when we were preparing the debate, we said that we will start with questions among the two of you. If
maybe we go, just me or both?
the two of you.
Ah, come, Gil. Are we going to sit down or are we going to stand? We're going to stand. We just stand there. Oh, questions between us?
Between the two of you.
Sorry.
Should I ask? I can ask.
Ask a question about this presentation, what that was made, this last one. I mean,
Absolutely. So 1 minute. Let's.
well,
Go ahead.
so it seems like you said.
Is it
that
maybe switch it on?
So you seem to have indicated that there are some fundamental obstacles which you several times referred to that would sort of retard this claim or make it nearly impossible, almost impossible. But you said absolutely nothing concrete. You just said several things like you sort of said, it's like building a straw man. You said some people say something and that was incorrect. But what is your fundamental objection? What is the nature of your fundamental objection? I mean, that's my question.
Sorry, is this debate between you and them? Or you take this one.
Yeah, I think I indicated the theoretic, but certainly I didn't detail it. As a matter of fact, in this presentation, I presented 20 slides, including the thank you, but there are 80 slides which elaborate on each part of the claim, in particular about my argument. But what I said briefly is that I analyze the computational complexity power of noisy intermediate scale quantum circuits, and I realize that this computational power is described by a computational class called LDP, which is very low-level computational class. So this is the crux of the matter.
Is there any way you could bring that back?
Yeah, of course.
Sure. Maybe. Yeah.
It's important.
I don't know how I can bring it. No, it's not this one. No, let me. Okay, maybe since I got this slide by mistake, I want to mention that this is not Duel in the militant way. Okay, and this is not really a duel, and certainly not a war,
actually.
and it's a fantastic scientific debate. Okay, it just popped up, and I want to emphasize it. Yeah. But let me go back to the place where this is explained. This is the crucial prediction. So let me repeat it. If you start with NISQ devices, and this is precisely what IBM and all the other companies, Quantinuum, Google, are trying to build, then you get samples, and the samples are, they belong to a very low-level computational class that is called low-degree polynomial. It means that those are probability distribution that can be described by polynomial of bounded degree that does not depend on the number of qubits. Now, this computational class, LDP, is very low-level computational class. And therefore, these devices can be regarded as classical computers, and not only as classical computers, but as very primitive type of classical computers. And this heuristically implies that they cannot achieve quantum supremacy. Why I say heuristically? Because in computational complexity, we deal with asymptotic claims, and when we implement them for a specific number, say, I don't know, 500, then it is always of heuristic nature. But this is the ordinary way that computational complexity is applied, except that in this case, it applies for engineering efforts. Usually, it's applied for programming efforts. So we know that a programmer cannot write an efficient program for solving NP-complete problems. Not because he's a bad program, but because there is inherent obstacle. And I claim that the engineer cannot reduce the rate of errors for qubits and for gates, not because he is a bad engineer, but because there is a fundamental computationally complexity obstacle.
Thank you.
And this adds to the fourth argument.
Yeah, thank you very much. And let's give word to Matthias.
Okay, well, thanks a lot. I think it will be very nice for me to understand. You make this one claim, which is very specific, that you cannot reduce the noise, the gate noise, below a certain threshold, right? And that, if true, might actually present an obstacle, right? I'm sort of like agreeing with that. But what is the number? Because I mean, once we have the number, we have it now on tape, and then we can see in a few years, we meet again, and we see, did we beat this number? Yes or no, right? Because if we don't keep it concrete, then, you know, we can shift the goals as we move along. So what is this number?
Yeah, I'll tell you what's the number. I should say that we can moderately shift the goals from time to time. We don't, but you see, if you follow this argument, which comes from computational complexity, then you wouldn't, I can tell you what I expect to be the number, but usually computational complexity, they tell you that nobody will ever be able to build a machine that computes the permanent for arbitrary matrix. Now, probably the number that is already beyond reach is something like 500 or 1,000. And we can agree on this number, and probably we will be right. But computational complexity doesn't give you a precise number. It gives you an indication. So, and by the way, for permanence computation, even quantum computers will not help. We also agree on that. So this is a similar situation. The argument is indirect. It says this computational class will not be able to achieve quantum supremacy. Okay, so this is the first. And because quantum error correction is more difficult than quantum supremacy, this is a sort of a common knowledge among engineers and people, experimentalists, then we will not be able to achieve quantum error correction, and therefore there is a limitation on the errors for 2 gates, for 1 gate, for qubits. What is the error? What is the ratio? If you want something that will not be, you will not see disproved. Certainly, what people try to do now is to get a gain of something like 6, 7 order of magnitude in existing, and in my opinion, they will not gain 2 order of magnitude, and I even doubt if they'll gain 1 order of magnitude. So now the 2-gate error, of course, things depend from one platform to the other, but you will not gain 2 order of magnitudes compared to.
Okay, so if we make this precise, so at the moment we are basically at 10 to the minus 3, roughly, right? 0.1% error. Okay, so maybe, okay, so we fix it, but whatever the platform we now fix, either superconducting, say, or ion-based, you're saying we will not see an improvement by 2 orders of magnitude.
Right.
Okay.
Thank you very much. So, the two of you, do you have other questions just between the two of you, or shall we get questions from the audience?
Yeah, so now that I got this number, usually when you usually when you get this number, it doesn't sort of like it. Usually when you propose a theory that like, don't you want to stay? Oh, be careful. You just okay. So then this number kind of like comes out of a theory, right? So there should be somehow, it should come out of some kind of modification of quantum mechanics, right? It should come out of some kind of microscopic theory. How did you compute this number?
Okay, this is again a good question. So physicists, not only that they don't agree with this, they have a pre-assumption about what should a theory that will enforce impossibility of quantum computer will look like. So first of all, everything I said is within quantum mechanics. There's no modification, no correction. Not only that everything I say is within quantum mechanics, I use precisely the same models that Aronov and Ben-Or used for their threshold theorem. Now, the argument for this prediction, specific number prediction that I made, is based on a computational complexity argument and my intuition about how it's going to behave. But, and this is the number. So it is based on computational complexity. It's like how large is a matrix that we can hope to compute the permanent. So I don't know, what is your guess? What is your number? 500, 1,000, 2,000?
But you're saying that you adhere to standard quantum mechanics, but I don't know any limit in standard quantum mechanics that you couldn't go below. So where does it come from? It must come from some additional assumption in addition to quantum mechanics.
No,
so how do I have to square these two things?
First of all, this is also a good question. But you see, in all the study, we make additional modeling on top of the quantum mechanics. In all the study of noise and errors, we say we have noise, we want to make, we have some assumption about the way the noise behave. The noise represent the interaction of your quantum system with the environment. So this is within quantum mechanics, yes. And the question is the intrinsic lower bound for the level of interaction of a system with the environment. And I claim there is such a lower bound. It's based on computational complexity argument. So let's take quantum mechanics, you add to it certain modeling of the noise, which is modeling we agree, and then you add some computational complexity analysis.
Let me actually ask, because there is just somehow not to somehow interrupt you. I organize it, so I just do. Actually, because that's something which I am curious about, why these quantum computers don't exist in nature.
You ask him or me?
Both of you. Actually, also you, yeah, Gil. And okay, then Matthias, let's say.
Well, first of all, this is a very good question. Whether nature has some sort of A, quantum error correction, B, quantum fault tolerance, and C, quantum advantage. Now, it is reasonable to think that there is no example in nature for quantum error correction and quantum fault tolerance. It is reasonable to think so. And we actually, this is something that with Dorit and with some chemists and physicists we studied, we talked about. And also, I think it's reasonable, it's very hard to point your finger on things where there is something candidate for quantum advantage in nature. So in nature, as far as I know, there is no example of quantum error correction. There are, by the way, examples of classical error correction in nature, but not quantum error correction. There are no example of, and as far as I know, there's no convincing example of quantum advantage. There are examples, there are theories, and this was the motivation for quantum computers, like high energy physics theories, that the computation are very difficult. And this was the motivation for the idea of quantum computers. But this is not, as far as I can see, this is not a convincing demonstration of additional computational power coming from quantum physics, and this is a very interesting topic that we can discuss.
Matthias, what do you think about this?
Okay, so I think there's several ways of answering it. I mean, one is that I think there is a reasonable argument to be made that the universe is a quantum computer. So you could credibly, you know, maybe I'm trying to like specify your question more precisely, right? You could sort of like say, okay, well, whenever particles collide, there is an interaction, and in that sense, there is a computation being done.
But do you know a quantum computer in nature somehow? Yeah, high powerful quantum.
Yeah, so that's what I'm saying, right? So then I think you want to probably ask, do we have a, you know, why don't we see a fault-tolerant quantum computer in nature? And you know, we could ask the same question classically. You know, why has it not evolved? Why has now, you know, not evolved yet? That we you know, and I guess you know, there was enough evolution so that humans have built a classical computer, right? So now we see a classical computer in nature, right? And in that sense, the next step would also be like that we can build, that we who have evolved can build a quantum computer. So, you know, I think we will see it in nature.
So that yeah.
In the future.
You don't know one,
I mean, maybe it exists on some other planets.
But I think you ask about nature itself,
yes,
not
exactly.
About the artificial
nature itself.
Okay, so I think there is no evidence. There is, well, everything, well, first of all, everything is quantum. So my laptop is a quantum computer. The question is whether it has abilities beyond classical computer. The point of view that I have is that actually the quantum noisy world has very low level computation, and the only way to get any robust information and any robust computation is by a process which is an error correction process that lead to classical information. So classical information in nature and the fact that we are robust classical entities is based on some sort of error correction, which by averaging and by repeating give you robust classical information. This mechanism exists in nature even before we were debating, even before we were alive. This is something which is in nature all along. Whether there is something extra in nature, so I think it's fair to say there is no natural quantum error correction and quantum fault tolerance. Is there in nature quantum advantage, computational advantage? There are some arguments that maybe there is because it's so difficult for us to simulate quantum physics. But the fact that it's so similar, it's so difficult to us to understand something does not necessarily mean that there is some superior entity that explains it. There can be some other reasons, but I think one important consequence of the debate about quantum computers is the ability of digital computers to simulate quantum mechanics processes and quantum chemistry and so on.
Thank you very much, both of you. So let's get a question for Slido. So Ronald de Wolf asks the question which you can see. So noisy classical circuits are a special case of noisy quantum circuits. Its noisy quantum circuits can only compute some low-level complexity class. Then the same should be true for noisy classical circuits.
So I believe this is for me, right?
Yeah, I think it's for you. You definitely...
Okay, this is a hi, Ronald.
Also on my team.
What? This is a great question.
You brought an army.
No. This is a great question. I even have a slide in the presentation which explains. So, if I claim that quantum computing is impossible, what is the reason that classical computing is impossible? So, you have to look at this very primitive computational class, LDP. And LDP can do one thing. It can imitate the standard way of nature to create robust classical information. The standard way of nature to create robust classical information is repeat and then perhaps take majority. So we can approximate majority with LDP, we can repeat with LDP, and therefore the mechanism for the very basic natural way to achieve classical information and subsequently also classical computation is still supported by this low-level complexity class LDP for probability distribution. So this is a good question. This is certainly addressed in details in things I'm doing.
Thank you very much. And for Matthias, do you believe that Majorana zero mode can generate good quality qubits in practice?
I'm not an expert.
Okay.
I mean, this is basically Majorana zero modes. It's one technology that's put forward for producing so-called topological quantum bits. I think it's consensus in the community that we have not seen a single topological quantum bit, and I think it's still, it's out to be demonstrated, but, and then, yeah.
Very good, thank you. There is a question.
Let me take the skeptical to skeptical. What do you mean consensus in the community? The IBM and other groups, IBM declared achieving topological quantum computing. Not IBM, Microsoft.
Well, I mean, they have. There is a paper out on topological quantum computing. And I believe in that. It's not claimed that they can do a full all the single qubit operations, etc. So I don't think that's accepted yet that we have a full quantum qubit. I mean, they probably have milestones.
So you do believe that they can do what they write in the papers they can do?
I mean, the papers that they. I mean, yeah. Well, okay. So I mean, I'm not an expert on this technology, but I'm sort of now standing and saying, like, I'm defending the scientific community, and if these papers are published in peer-reviewed journals by experts, then the results that are published there, I believe, and I mean, maybe this comes to a second point. I believe that the quantum computing community is a well-functioning research community. So that means that, of course, like in any research community, and for any research results, there are only a handful of referees at most, right? Typically it's 2 or 3 that refereeing the paper, and of course this is, of course there can be flaws in the process, but in general, I think the community is well functioning also on the experimental side and can falsify claims put forward, right? So if we see something there, it will be rectified and corrected in the literature, like in any other scientific community.
Thank you. Let's take a question from the audience.
I will bring the microphone around. Anybody wants to ask a question here?
Thank you very much for the talk. Actually, I have two questions. First of your talk, you talk about inherent noise. Can you explain what are inherent noise? And then, if I understand you correctly, you also believe that there is some threshold for error, that below it, quantum computers can work. But actually, we couldn't get to below that threshold. And what are the reasons that we couldn't have that small errors? What fundamental aspect of physics don't let us?
So I think, as I said, the modeling of errors, which is the interaction of your quantum device with the environment, so the entire world is a quantum computer. I argued that even the entire world cannot factor numbers to the prime factors, but it is a quantum device, and the errors, the reason for the errors is that there is interaction between your device and the outside world, and this is magnified by the fact that you need to control the qubits and gates, and therefore you need to have some connection between the outside world and your device. So the question is if you can reconcile the fact that you need to control the way the qubits and gates behave, and that you need to isolate the device from the outside. And this is the question. And then the argument that I put forward, and this argument is based on the way that ordinarily we model quantum computers, is based on a computational complexity argument that says that these intermediate scale devices are, in fact, they are computationally very low level.
Thank you very much. So there is, in Slido, there is a question of Alexander Zykov, which I believe could share light to the crux of the debate. So let's assume that the noisy quantum circuits will never become noiseless. For both of you, could we still use these noisy quantum circuits as a guesser accelerator for a classical computation?
Yeah, I guess that is a question to this NISQ debate in some sense, if I understand correctly. I mean, there's two ways of interpreting the question, right? So I would interpret it in this way. Let me try both. Okay, so if I interpret in the sense that like a noisy quantum circuit, right? If the noise is below threshold, then actually with this noisy quantum circuit, I can simulate a noiseless quantum circuit, and then actually, you know, I can do it. So it has to be somehow the assumption here in this question that I will not manage to go below threshold, and is it then still useful? And I think that is the question that Gil mentions. That is almost the definition of a NISQ machine. Okay, so a NISQ machine is basically a machine by definition that is not a fault-tolerant quantum computer. It's like the opposite of a fault-tolerant quantum computer.
Maybe can you repeat for the audience what is NISQ machine?
NISQ just means it's just a quantum device that has not led to fault-tolerant quantum computing. Okay? That cannot be used for fault-tolerant quantum computing. So basically, I think this must be meant by that. So let's assume we have a machine where we are above threshold. Is it still useful? And I think there is different claims out there. There is this quantum supremacy claim, and then it becomes harder. Becomes harder to do. It's very hard for me. Like it's very hard for me to imagine this will happen. It's very hard for me to imagine that we will have this is again now, it's very hard for me to imagine we will build a machine that stays above threshold, does something non-trivial, but somehow doesn't reach fault-tolerant quantum computing. So it's very hard for me to imagine it will happen. You know, maybe for money reasons or time reasons, this just takes too long and we get bored doing other things and so on. But it's very hard to believe this on physical grounds this might happen. And then it might still be useful, right? There are claims out there. There's people researching on it. Then it's a little bit more in a heuristic regime, I think that.
Thank you. Gil, do you want to say something about this question?
Overall, I agree. I think. The crucial thing is to get better qubits, better gates, and better and good quality or very good quality quantum error correction. And if this cannot be achieved, I doubt if they will be used. And also, I think Matthias agree. And if this and I also doubt that this can be achieved.
So that is the point.
Can I add one sentence to the end? I was just rereading the question. For many applications, just knowing a rough guess. You see, if you're below threshold, then basically the errors will just accumulate. And then somehow, you know, why should it then be a good guess, you know? I mean, that might just be complete rubbish in some sense. So you kind of want to go below threshold and then you get the right result. Or else, you know, maybe it just accumulates. I mean, that would be sort of like my... But I mean, it doesn't mean that nothing useful can be done, and I think the supremacy claims are in that direction.
Thank you. So what about this anonymous question for Gil? In in 2024, Google demonstrated sub-threshold surface code that achieved the extension of a logical qubit's coherence time. Would this contradict your theory? If I read correctly the question.
We're talking about the first question?
It was yeah, that one, anonymous.
Yeah, I think this question was asked in the quantum computer questions and answer site, and it was answered by a guy from Craig Gidney from Google, and he thinks that in order for him to regard my argument as false, he would need an improvement of maybe 8 orders of magnitude over the existing. And then I immediately comment and I said, you know, Craig is too tough, and I will admit that I'm wrong even for 4 orders of magnitude. And even today I gave Matthias another order of magnitude, just that he will feel good. But so far there is a claim by the Google people that they can do with 7 surface code an improvement of some ingredient of the noise by a factor of 2. And I think, first of all, it needs to be scrutinized. And here, I don't fully agree. Well, it's not a matter of, the problem is not the community of quantum computing. In general, there is not enough scrutiny of experimental claims. I know this because we studied this Google paper from 2019, and this project is a 6-year project. It's very difficult, and often researchers don't share their data or don't share part of their data, and this is a delicate situation. So we have here a problem, not specifically about the quantum computing, perhaps it's a larger scientific problem that needs to be addressed, but it is an issue. The incentives and the enthusiasm is very high, and there need to be some skepticism.
We do scrutinize these papers. So when these papers come out, we do sit down and we look at them and we scrutinize them. I think a lot of people in the community do this. And I think we're extremely skeptical when new claims come up. I want to really defend the community there. So no, I think the answer to this question is no. But this is a very important paper. And the paper is a step towards that goal. And there are some technical details now about how the error correction is done, et cetera, of why I would now suggest we answer this with no, but it's an important step. And I think what we're seeing in this community is that there are very important steps being made, step by step. We're moving forward step by step, but, and actually, I think the progress is fast, but the road is very long. So.
Thank you. Is there a question from the audience? If yes.
I think it's good to mention the thing that is called expectation bias. So this is something that is very well known in experimental science, that people doing experiment, that they want the experiment to result in something particular, and then when it looks like they achieved what they did, they don't scrutinize properly what they did. I'm afraid that in every community, like in this quantum computer, there is a lot of expectation bias. I'm not saying that because I doubt that the computers will be built. I am an optimist, but it's very difficult to judge these results without bias.
Thank you.
Actually, can I respond to that? I totally agree. But you see, we actually, the situation gets better and better. So a lot of these devices are being made available in the cloud. And then, you can just log on and try them out. For some of them, maybe you have to pay something. But then you get access. And then, of course, I mean, they might put some other machine there, and it might be, but that would be fraud, right? So I'm accessing, I can access not the latest device, not this particular device on which this particular claim now was displayed there, but I can I can actually access earlier devices, and we're doing this. And so we are scrutinizing, and if they put out a number, then we're running our benchmarking system on it, and we can actually see, you know, oh, is that number right? Oh, maybe it's off by some factor, etc. So, but I agree. I mean, but I think you know, it's still.
Let's then Pavel and Gil want to say something.
Maybe I just want to say that I didn't check carefully the Google claim about surface code. I checked carefully the earlier claim of 2019 about quantum supremacy, and yeah, I think things should be checked, and I'll be, and not only checked, also it's interesting science to study probability distribution coming from quantum computers, and if Matthias has samples that he can get on the cloud, I'll be happy to get them and to analyze them in my tools.
Thank you. Let me ask, because there was a question which disappeared from the board, from Laura, a person who gave recently Strouhalle lecture. Can you get to it? That was a question which I liked. And Marek Novotný, Strouhalle lecture. It's there, yes, perfect. So that's a question, I guess, for both of you. Can each of you, yeah, it's about adiabatic quantum computers in 2017, huge advance or all hype. Can each of you give your probability, just speak about quantum computer will exhibit quantum utility within 10 years? That maybe you, it's all the same question if you speak about it, but go ahead if you want to, yeah, specify something or just.
What is quantum utility?
Yeah, relevant quantum computing, let's say this supremacy, quantum supremacy. Maybe we spoke about it. Maybe it's not such a good question after all. Sorry.
I mean, you know my favorite one, right? That's factoring. So.
Factoring. All right. Very good.
10 years. I'm not sure.
10 years.
Well, I mean, we'll see some factoring in 10 years. But whether or not you can not do that with a normal computer, I don't know.
So how large numbers you think we can factor in 10 years?
I don't know.
You asked me.
I asked you. Well, but I mean, you know, like, you know, it was, I mean, I don't know.
20-digit numbers? 20-digit numbers?
We'll see.
Well, that's not very large.
I'm not pushing it.
I'm in the business of science, not in a horoscope writing. So.
Okay. So other questions? Yes.
So if I understood correctly, you made a very Gil, you made a very precise argument that these NISQ machines compute a very low degree polynomial class, which is very weak. So you can't really hope to do something better. My question comes from a place of non-expertise. Why isn't this considered a open and shut case? Then why do we have debate? Why is that argument dismissed by the experts?
Well, first of all, I regard this argument as good, but not as definitive argument. It uses some novel idea of using computational complexity for talking about engineering barrier. This is something that goes against people's intuition that believe that engineers would enable to reduce the noise level indefinitely. And I think this is a question which better be asked to other people. But I understand, you know, people have some prior, not only that they have great enthusiasm that quantum computers can be built, but they have some prior ideas about the kind of physical obstacles that may occur. And I understand that. it's a slow process of examining matters, and I hope we contribute to this process, the two of us, and also not only to the process, but also to the culture of the process. So although we maybe annoyed each other a little bit, but we kept a very good spirit.
Let me, because...
Please keep them distance there. Yeah. But I'm not really sure if I get this point of talking about NISQ machines the whole time. The point is whether or not we can build a fault-tolerant quantum computer. NISQ machines, by definition, not a fault-tolerant quantum computer. Now, you're making this argument that, like, a NISQ machine has a low complexity. Fine, okay? So, like, you know, I'm not debating that point, right? Because we're debating whether or not we can build a fault-tolerant quantum computer, not whether or not what the complexity of a NISQ machine is. So you know, and you put a connection there somehow, right. And it would actually be nice to scrutinize that connection.
Good, good. This is precisely why we are here. So I argue that NISQ machines, that this low-level ability of NISQ machine will not enable them, first of all, to demonstrate quantum supremacy, because quantum supremacy, even for 100 or 500 qubits, means that this machine can do computation that classical machines cannot do. And if we analyze this machine in this range and we discover that it's a very low level, then we should expect that it cannot achieve quantum supremacy. And then this is the first argument. The second argument is that quantum fault tolerance or even good quality quantum error correcting code is harder for NISQ to achieve than quantum advantage. The level of noise you need for demonstrating quantum supremacy is higher than the level of noise needed for quantum error correcting, for good quality quantum error correcting. And therefore, if you agree with me that these machines cannot achieve quantum supremacy, computational advantage, then there is another argument, appealing argument, again, not definitive, that it will not be able to build the good quantum error correcting code that are needed for quantum fault tolerance. So quantum fault tolerance needs two scales, success in two scales. It needs the ability to build quantum error correcting codes in the NISQ scale, and then to use them in the large scale to build fault tolerance. And I claim that in the NISQ scale, you will not be able to build good quality quantum error correcting.
Also, let me just say something for this question of Hans, which I think is exactly in the crux of this, why is it an engineering problem? And it is that the complexity classes are defined asymptotically. So while here critical are actually relatively small numbers, right? And so basically constant complexity solves everything with fixed numbers, right? You don't need low degree polynomials. Here that's the problem, that of problem and challenge of this argument of using complexity theory. If I understand it correctly, please correct me, because it's defined asymptotically, while here the problem is about relatively small numbers.
Yeah, I agree. Also, for the guy who asked why people are not convinced and stop doing anything, this is not what I advise. I think I have a good argument. They should take a note of it. They should also take note of earlier argument of different natures and move on, and we'll see where things are leading to.
Thank you very much. Do you want to add something, Matthias? Or is there some other question in the audience? Yes? Yes.
It's the second. The first question I answer with the... It's the second. It's when you add, it's an exponential increase.
Again, this question comes from an absolute non-expert in the subject, but can you maybe elaborate again kind of what the significance of the intermediate scale quantum system is in your computational complexity argument? So assuming that you can actually not kind of decrease the gate error rate by, let's say, 10 to the 2. This is kind of what we claimed, right? But just assume that's possible, and then we're actually able to build like noisy, large-scale quantum systems. Would anything sort of qualitatively change about your complexity argument?
I think nobody argued that not only we can build noisy, large-scale people, you know, IBM and maybe Duel, they build large-scale noisy quantum computers, but without quantum error correction, these computers, and I think Matthias explained it very well, they are not good for anything.
Okay, but large scale meaning in this case?
Large scale means many qubits. Many qubits are not useful unless you can, as far as we know, unless you can implement quantum fault tolerance. Quantum fault tolerance require high quality quantum error correcting code, very high quality, and I claim that even moderate, that high quality, much better than now, 2 orders of magnitude, 3 orders of magnitude cannot be achieved. This is the argument. As I said, it has some heuristic ingredients. I don't advise everybody just to quit working on this, but this is argument that people should take a note. We have plenty of ways to test things experimentally, and we'll see how it goes.
Okay, thank you.
I would like to answer the last question on the sheet. It's fantastic, because I didn't claim that we're quantum computers. I said you might regard the universe as a quantum computer, but what you need in order to factor, right? What you need in order to factor is a fault-tolerant quantum computer. I did not claim that we have a fault-tolerant quantum computer. So yeah, that's what you need.
I wonder, assuming the completely optimistic point of view, so assuming that we can build scalable quantum computers without limits, would it mean that eventually we will be able to observe non-trivial superpositions of macroscopic systems?
Yes. I mean, eventually. Yeah. But yeah, because basically, if you build a, depends how big your computer is, right? I mean, we have a definition of quantum computer. Now, it depends what you mean by macroscopic. If you say macroscopic 10 to the 23, right? Then, of course, you first need to build a quantum computer that has 10 to the 23 logical qubits. Right? And then you can do, and then you can in this logical subspace, you can prepare a superposition of, say, all 0 and all 1. And that would be, by all possible definitions of macroscopic entanglement, that would constitute macroscopic entanglement, yes.
I had in mind some kind of, you know, this old-fashioned philosophical objection of Einstein, like having my bed in a superposition.
Yeah.
So that would be, like, in principle possible.
Yeah, I think, yeah, it's possible. But you have to still keep in mind that that this object that's in superposition is then essentially isolated from the rest. So in that sense, you have it, and you can verify that you have it. And so, but it is like with Schrödinger's cat, right? It's sort of like, yeah, but in principle, right, you should be able to put, you know, a cat, right, like the state of a cat into dead and alive in a quantum computer, if that quantum computer has as many you know, qubits as needs to describe the state of a cat. You know, it's like yeah. But then, of course, you can't observe it, right? Then, in order to observe it, you would have to make a measurement, and in that moment, you know, that state would then collapse again. But you can probe the state in different ways. But yeah.
Thank you very much. What a science fiction question, very interesting. Is there, I wonder if there is some, if some physicists or is present, if there is some physics view of this duel, which somehow is some argument which was not put forward yet.
Do we have a physicist here?
For sure, but if there is some...
Who wants to ask a question?
Can you show hands? Who studied computer science? Who studied physics? Yeah, okay, there are a bunch. Who studied mathematics?
Yes, so do you want...
Chemistry.
Thank you.
Biology. Okay, very good. Philosophy.
Well, so I have one physics aspect that hasn't been discussed. Now the implementations that we have are very energy inefficient. So in order to make them, if we just simply rescale the existing quantum implementations, then they would be enormously hungry for power than classical processors we have. So that's the engineering problem that we will be facing soon.
Is that so?
Well, if I look at the trapped ion, for example, for flipping a qubit, you need several electron volts. Yeah, so semiconductors, I believe, are not like that. I cannot tell from top of my head, but...
But keep in mind that in order to for the system not to be exactly simulatable on a classical machine, you can already at 40 plus qubits, right? It'll become challenging to simulate it. So it's not clear that you need, you know, billions. Like our phones have billions of transistors, and but it's not the case that you will need billions of logical qubits in order to achieve something that you cannot achieve classically. So the speed up is exponential. Some speed ups are exponential. So you need vastly fewer, right? So and then, you know, the argument with, hey, here's the ion trap. And it's, you know, like, yeah, it has only dozens of qubits, but the proposal for the ion traps, for instance, could be that I take several of them and I connect them, right? And then, you know, maybe I only need 100 of them, I don't know, right? And then in order to achieve, you know, maybe each ion trap holds one logic qubit, I only need 100 of them, maybe let's say 1,000, but then it's not like some outrageous number that I have multiplied this by. And I think this argument also goes for, say, superconducting qubits, etc. So as soon as you go below threshold, the simulation is efficient. Maybe you need more qubits to simulate, to do Shor's algorithm or so, but in any case, so it's not clear, I think it's not clear that we will hit it on the energetic level.
Thank you. And maybe
I
last
agree
question.
with
Yeah.
I also agree. I think once we have 40 logical operating qubits, then this will be a very significant milestone.
Thank you. Mark Mezar.
I would like to ask, to get back to the question of the quantum device. You started, Matthias, you said, let's start with trying to define what is a quantum computer. It's very hard. So we already have quantum devices which are very efficient if we want to measure gravity to an extreme precision or whatever. I mean, there are many of them. And it might be that the quantum computer, the ones that we are building and the one that will be seen in the next 50 years, they will achieve something which will be a kind of niche computation, like a quantum device in some sense, dedicated to some very specific computation, which is very, very far from a universal computer and which will not at all be a substitute for the computers that we have. I would like to know your point of view about that.
So there are again several aspects to it. Yes, simulating a classical machine on a maybe simulating a classical machine on a quantum computer, of course, would be not something we want to do. So maybe the first thing for the next decades to think about is the quantum computer being a coprocessor that can do specific tasks. So I agree with you on this. A specific task could be where we have this exponential speed up, like in chores or in, I don't know, chemistry, I don't know what. So a few other of these cases. What I'm skeptical about, in respect to your question, is that we will be able to build a use, and I answered actually similar to an earlier question. I'm skeptical that we'll be able to build a really useful, even niche useful quantum computer that will not also be universal, at least in our computational sense. So it might still be that it will only be used for specific algorithms or for specific instances, but I think in principle it will be capable of running the others. But that doesn't mean that it will not be like a niche product. So yes, it could be that way. It could be that we end up with a quantum computer, it's a niche product, like other quantum devices with niche products, and it may actually more generally be true for the search for new quantum technologies. We have now narrowed this debate to fault-tolerant quantum computing. I think that's a wise choice. Otherwise, we would.
Thank you. Gil, do you want to add something?
Yes, I agree. I think with fault tolerance, even for a moderate number of logical qubits, we will see things we didn't see before. But without fault tolerance, I think this type of devices, quantum circuits, will not be useful.
Thank you. And time is up. Do you want, so both of you have possibility to add some very short message?
I think this was a very nice discussion. Let me say that the common view in the community is Matthias' view. There is much optimism. I think that there are serious reasons to doubt the possibility of quantum computers. There are some more details in the background for this debate and the small videos we prepared, and I'll also put online the full slides that I only got 20% or 40% of. And I think it's very important to learn this topic. It is exciting mathematics, exciting physics. On the matter of scrutinizing experimental quantum work, I think this is a problem, a general problem, maybe not only experimental, maybe also theoretical. Science is vastly expanding. Looking at a paper and trying to find a mistake is very, you have to invest a lot of effort, and it's fairly thankless task. So we need to find ways to improve this, and I think most important, we need to find a way to live in uncertainty, not only about big questions, but also about specific claims. You know, people claim enthusiastically all sorts of claims, and we have to understand that we will live in some uncertainty, both about the big problems and about some specific claims.
Thank you. And Matthias?
Well, I think the field has come so far that you can scrutinize all of this yourself. And I really want to encourage all of you to do this. Like some small devices are for free on the cloud. You know, IBM has something, and others I'm sure will follow. Or to do your first step, it's easy. Okay, this is not difficult. So you just go and try to scrutinize it yourself, rather than maybe listening to a debate. So you could just do that, and the field will expand, and these options of accessing these devices in the cloud expands. You don't need to be an expert in trying to, hey, see what is the noise rate of this qubit. Oh my God, was that terrible, right? You're going to come back. And it's like, oh wow, he told me 0.1%. Actually, it was 5%. But hey, it was maybe 5% and not, it did do something, right? And then you can follow the progress yourself. I think I really want to encourage you all to do that. It's fun, and it's sort of like debunks a lot of the thing, because when you read it in a newspaper and so on, it's like meta of meta and like just hyped and so on. But like, you know, you're scientists, you know, get to the ground.
Thank you very much. Let's thank our duelists for this wonderful discussion. And let me actually invite you for tomorrow, when this program of the celebration meeting of Learned Society continues. Tomorrow we have Prague encounters in mathematical physics faculty in Malostranské náměstí. It starts 2 p.m. by colloquium of Mark Mezar, following lecture of Lenka Zdeborova and a lecture of Annie Cohen-Solal. And so come, it will be extremely interesting, and that's it for today.